Welcome to The Explainer. Today, we're going to talk about a serious upgrade for your Precalculus toolkit, the Law of Cosines. Look, if you've ever found yourself stuck with a triangle that isn't a right triangle, yeah, this is The Explainer for you.
So here's the plan. We'll kick things off by seeing why we even need this law, then we'll get into what it actually is. After that, we'll run through a couple of examples, talk about how to get really good at it, and wrap up with where you see this stuff in the real world. All right, let's jump right in. We're going to start with something you already know really well and show you exactly where it falls short. You know the drill, right? Pythagorean theorem. A squared plus b squared equals c squared. It's awesome, but it's got one huge catch. It only works for right triangles. You know, the ones with that perfect 90-degree corner. So what about literally every other triangle out there? What do we do then? And that is where this new tool, the Law of Cosines, becomes a total game changer. It takes us beyond just that one special case and lets us tackle any triangle you can throw at it. It's like going from a basic wrench to a full-on socket set for your math toolkit. Okay, so let's get to the main event. Let's look at the law itself, and you'll see how it's kind of like Pythagoras' bigger, cooler cousin. All right, here it is, and look, the first part should look super familiar, right? A squared equals b squared plus c squared. That's just Pythagoras. But then you've got this little extra bit tacked on the end, the minus 2 bc cosine of a. That little piece right there is the secret sauce. It's the correction factor that makes the whole thing work for any triangle, not just the right-angled ones. Now, don't freak out seeing 3 different versions. You don't have to memorize 3 things. It's actually just one pattern. See how this side on the outside, like a squared, matches the angle on the inside, cosine of a? That's all it is. The side you're solving for and its opposite angle are the bookends of the formula. Simple as that. And here is the coolest part. This is how you know it's really just an upgrade to Pythagoras. What happens if we plug in 90 degrees for the angle? Well, if you remember your unit circle, the cosine of 90 is 0. And what happens when you multiply anything by 0? The whole back end of the formula just vanishes. And what are you left with? C squared equals a squared plus b squared. It becomes the Pythagorean theorem. It's not a different rule. It's the master rule that Pythagoras is just a special case of. How cool is that? Okay, so the big question is, when do you actually use this thing? It's really specific, which is good. You're going to reach for the law of cosines in 2 main scenarios. First, side angle side, or SAS, when you know 2 sides and the angle squished between them. And second, side side side, or SSS, when you know all 3 sides and need to find an angle. All right, enough theory. Let's actually put this tool to work. We're going to walk through one of each type of problem so you can see exactly how it's done. Okay, first up, a classic side angle side problem. We've got side B equals 7, side C equals 10, and the angle tucked right between them, angle A, is 60 degrees. The goal? Find the length of side A over there, the one across from the angle we know. This is just a plug and chug, really. Step 1, pick the right version of the formula, the one starting with a squared. Step 2, substitute everything we know. So 7 for B, 10 for C, and 60 for A. Step 3, just crunch the numbers. You get 49 plus 100 minus 70, which gives you 79. But wait, that's a squared. So the final crucial step, take the square root. And you get your answer for A, roughly 8.89. Okay, example 2. Now we're dealing with a side, side, side situation. We've got all the sides. A is 5, B is 7, and C is 10. But we don't have any angles. Our job is to hunt one down, and we're going to go for our angle C. Now this one starts a little differently. We can't just plug things in. First, you got to do a little algebra on the formula to get cosine of C all by itself. But once you've done that, it's the same old story. Plug in your numbers, calculate the value, and hey, look at that, you get a negative number. Don't let that throw you off. It's a huge clue. It just means the angle is going to be obtuse. The last step is to use the inverse cosine button on your calculator, and boom, angle C is about 111.8 degrees. Okay, so you've seen the basics. Now let's level up. We'll talk about how to tackle more advanced problems, and more importantly, how to avoid the easy mistakes everyone makes. Listen up, because these are the 2 things that trip people up all the time. First, forgetting to take the square root at the end. Remember, the formula gives you a squared, not a. It's such an easy mistake to make. The second one is freaking out when the cosine comes out negative. It's not wrong. It's your calculator telling you that you're looking for an angle bigger than 90 degrees. Just trust the process.
All right, let's look at a more advanced problem, the kind where you're asked to solve the triangle. That means find all the missing parts. We're given two sides and an angle, and we need to find the third side and the other two angles. This is where you have to be smart about your tools. You have to start with the law of cosines. There's no other way to find that first missing side. But here's the pro tip. As soon as you find side C, you now have a side and its opposite angle. And that means you can switch over to the law of sines, which is way faster for finding the next angle. Once you have two angles, the third one is a piece of cake. Just subtract the two you know from 180. So you might be thinking, okay, great, but when am I ever going to use this? Well, it turns out, all the time. Triangles are everywhere, especially in things like engineering, surveying, and navigation. Let's look at one really concrete example.
I mean, this isn't some abstract textbook problem. It's literally how pilots navigate. Imagine a plane trying to fly straight, but there's a strong wind pushing it from the side. The plane's path, the wind's path, and the actual path the plane travels over the ground. That forms a triangle, and it's almost never a right triangle. Pilots use the law of cosines to figure out exactly how to correct for that wind to make sure you land in the right city.
So, what's the big takeaway here? You've just added a seriously powerful tool to your math arsenal. You're not stuck with just right triangles anymore. You can basically solve for any missing piece of any triangle. So the real question now is, what can you measure in the world around you? The distance to a ship at sea? The height of a mountain? The possibilities are pretty much endless.